Hi, welcome. I didn't really know what to do with this, but I needed to read a meteorology chapter. So here we are. I actually like meteorology, like it or not. So this will be fun for me. I don't know about you, but you say you watch it 2 times as fast, so you're gonna get some fun little facts. Our atmosphere is a delicate, life-giving blanket of air that surrounds the fragile Earth in one way or another. It influences everything we see and hear. It is intimately connected to our lives. Air is with us from birth, and we cannot detach ourselves from its presence. In the open air, we can travel for many thousands of kilometers in any horizontal direction. But should we move a mere 8 kilometers above the surface, we would suffocate. Isn't that fun? What a fun little fact. We may be able to survive without food for a few weeks, or without water for a few days. Okay, this is boring. I don't care. The atmosphere and the scientific method. I already know that. Something actually interesting. Let's see. Weather watch? Okay, well, we're getting somewhere. Composition of today's atmosphere. How fun. Table 1.1, which I would show you, but I'd have to pick up the book. And that's... Sorry, they like to talk a lot. Okay. At the surface, there's a balance between destruction output and production input of these gases. For example, nitrogen is removed from the atmosphere primarily by biological processes that involve soil bacteria. In addition, nitrogen is taken from the air by tiny ocean-dwelling plankton that convert into nutrients that help fortify the ocean's food chain. Fun. It is returned to the atmosphere mainly through the decaying of plant and animal matter. Oxygen, on the other hand, is removed from the atmosphere when organic matter decays, and when oxygen combines with other substances, producing oxides, it is also taken from the atmosphere during breathing. Look at that. It full circle. Coming right around. Breathing. Same thing. As the lungs take in oxygen and release carbon dioxide, CO2, the addition of oxygen to the atmosphere occurs during photosynthesis, as plants, in the presence of sunlight, combine carbon dioxide and water to produce sugar and oxygen. I don't want to watch this. Okay, we're going to skip a little bit, because this is really boring. I just want to read... Oh, air pressure. I'm getting that. Earlier in this chapter, we learned that most of our atmosphere is crowded close to the Earth's surface. The reason for this, in fact, that air molecules, as well as everything else, are held near Earth by gravity. Fun. The strong, invisible force pulling down on the air compresses air molecules closer together, which causes their number in a given volume to increase. The more air above a level, the greater the squeezing effect or compression. So air in very high, more squeeze. Gravity also has an effect on the weight of objects, including air. In fact, weight is the force acting on an object due to gravity. Weight is defined as the mass of an object times the acceleration of gravity. Thus, weight is equal mass times gravity. This is some PTSD. I took physics for 2 years in high school, and I don't like these. I don't like these numbers. As an object's mass in the quantity of matter in the object, consequently, an object's mass in the quantity of matter is the quantity of matter in the object. I can read. Consequently, the mass of air in a rigid container is the same everywhere in the universe. However, if you were to instantly travel to the moon, where the acceleration of gravity is much less than of Earth, the mass of air in the container would be the same, but its weight would decrease. Fun fact, gravity was equal to 9.81 meters per second. That's probably not the right units. There you go. Fun little number that's stamped on my brain. An object's mass. When mass is given in grams, g, or kilograms, kg, volume is given in cubic centimeters, centimeter cubed, or cubic meters, meters, m3, m cubed. Near sea level, air density is about 1.2 kilograms per cubic meter, nearly 1.2 ounces per cubic foot. The density of air, or any substance, is determined by the masses of atoms and molecules and the amount of space between them. In other words, density tells us how much matter is in a given space. That is volume. We've expressed density in a variety of ways. The molecular density of air is the number of molecules in a given volume. Most commonly, however, density is given as the mass of air in a given time, or in a given volume. Thus, density is equal to mass divided, or mass over volume. Because there are air molecules are in constant motion. On a mild spring day near Earth's surface, an air molecule will collide with about 10 billion times each second with other air molecules. Sounds like a rave. It will also bump against objects around it. Houses, flowers, trees, the ground, and even people. Each time an air molecule bounces against a person, it gives a tiny push. This small force push, divided by the area on which it pushes, is called pressure. Thus, pressure is equal to force over area. I think we get the idea. I'm gonna skip. It's an online class, it's fine. The layers of the atmosphere. Okay. Up to this point, we've looked at how both air pressure and density decrease with height above Earth. Rapidly at first, then more slowly. Air temperature, however, has a more complicated vertical profile. What a sentence. Crazy. If you look at the figure and notice that air temperature normally decreases from Earth's surface up to an altitude of about 11 kilometers, which is nearly 36,000 feet or 7 miles. This decrease in air temperature with increasing height is due primarily to the fact that sunlight warms Earth's surface, and the surface in turn warms the air above it. Wow. Imagine that. The rate at which air temperature decreases with height is called the temperature lapse rate. The average or standard lapse rate in this region of the lower atmosphere is about 6.5 degrees Celsius for every 1,000 meters, or about 3.6 Fahrenheit for every 1,000 feet risen in elevation, for about every 1,000 feet rise in elevation. Keep in mind that these values are only averages. On some days, the air becomes colder more quickly as we move upward. This would increase or steepen the lapse rate. On other days, the air temperature would decrease more slowly with height, and the lapse rate would be less. Occasionally, air temperature may actually increase with height, producing a condition known as temperature inversion. It's bolded, I guess it's important. So the lapse rate fluctuates, varying from day to day, season to season, place to place. In figure 11, you're not missing much. It's just like some colors, and it shows little spears. It's fun. So I get the idea. Okay. Lapse rate, that's fun. I promise I don't actually study like this. I just don't care. Let's see. Brief review. Weather and climate. Oh, this will be fun. Air temperature, the degree or hotness or coldness of the air. Hot is actually just or is it the other way around? I believe it's cold that's just an illusion. In fact, it's just a varying level of temperature. I don't remember the Don't quote me on that. Air pressure, the force of the air above an area. Humidity, a measure of the amount of water vapor in the air. Clouds, visible masses of tiny water droplets and or ice crystals that are above Earth's surface. I've always wanted to eat a cloud. I don't know about you. It makes no sense because it would just be like a little bite of water, I guess. Precipitation, any form of water, either liquid or solid, rain or snow, that falls from clouds and reaches the ground. Visibility, the greatest distance one can see. Wind, the horizontal movement of air. Crazy. And then let's move on to the next chapter. Ooh, we're getting into fun stuff. Alright. Storms of all sizes. Probably the most prominent feature in, I don't know where the figure is. Well, it's a shame. Is the white cloud masses of all shapes and sizes. The clouds appear white because the sunlight is reflected back to space from their tops. The largest of the organized cloud masses are the sprawling storms. One such storm appears as an extensive band of clouds over 2,000 kilometers long, west of the Great Lakes. Superimposed on the satellite image is the storm center, indicated by the large red L, and its adjoining weather fonts in red, blue, and purple. Got purple up in there. The middle latitude cyclonic storm system, or extratropical cyclone, big boy hurricane, forms outside the tropics and in the northern hemisphere, has winds spinning counterclockwise, but its center, which is presently over Minnesota. A slightly smaller but more vigorous storm is located over the Pacific Ocean, near latitude 12 degrees north and longitude 116 degrees west. This tropical storm system, with its swirling band of rotating clouds and sustained surface winds of 65 knots. Oh, I know what knots are. Or 74 miles per hour. Probably should look up what knots is. Me. Or more is known as a hurricane. The diameter of a hurricane, as measured by the presence of winds of at least 34 knots, 39 miles per hour, is about 800 kilometers, 500 miles. The tiny dot at its center is called the eye. Near the surface and the eye, winds are light, skies are generally clear, and the atmospheric pressure is lowest. Around the eye, however, it is an extensive region where heavy air and high surface winds are reaching peak gusts of 100 knots. Fun. Smaller storms are seen as white spots over the Gulf of Mexico. These spots represent clusters of towering cumulus clouds that have grown into thunderstorms. Now I'm interested. That is tall, churning clouds accompanied by lightning, thunder, strong gusty winds, and heavy rain. If you look closer at figure 1.16, you will see similar cloud forms in many regions. There were probably more than 1,000 thunderstorms occurring throughout the world at the very moment. Although they cannot be seen individually, there are even some thunderstorms embedded in the cloud mass west of the Great Lakes. Later in the day on which this image was taken, a few of these storms spawned the most violent disturbance in the atmosphere. Tornadoes. Fun. I love tornadoes. When I was little, I would watch Storm Chasers, and that's all I would do. My parents hated me. That's all I heard was Storm Chasers. I can recite every single episode. Am I proud of that? It's a fact, though. Let's see. Well, I'm bored of that chapter. Chapter 2. Energy. The warming Earth and the atmosphere. By the definition... Hello. By the definition, energy is ability or capacity to do work on some form of matter. Matter is anything that has mass and occupies space. Work is done on matter when matter is either pushed, pulled, or lift over some distance. When we lift a brick, for example, we exert force against the pull of gravity. We do work on the brick. The higher we lift the brick, the more work we do. So by doing work on something, we give it energy, which it can, in turn, use to do work on other things. That brick that we lifted, for instance, can now do work on your toe by falling on it. That happened to me. I used to work at Home Depot. My whole nail split. It was gross. There you go. Another fun fact. The total amount of energy stored in any object, internal energy, determines how much work that object is capable of doing. A lake behind a dam contains energy by virtue of its position. This is called gravitational potential energy, or simply potential energy, because it represents the potential to do work. A great deal of destructive work if the dam were to break. The potential energy, PE, of any object is given as PE is equal to mgh, where m is mass, an object's mass, g is the acceleration of gravity, and h is the object's height above the surface. Isn't that fun? Then we go into temperature scales, which Fahrenheit's stupid, you get it. The transfer of heat from molecule to molecule within a substance is called conduction. Hold on one end of a metal straight pin between your fingers and place a flaming candle under the other end. Okay. Because of the energy they absorb from the flame, the molecules in the pin vibrate faster. The faster vibrating molecules cause adjoining molecules to vibrate faster. These in turn pass vibrational energy onto their neighboring molecules, and so on, until the molecules at the finger-held end of the pin begin to vibrate rapidly. These fast-moving molecules eventually cause the molecules of your finger to vibrate more quickly. Heat is now being transferred from the pin to your finger, and both the pin and your finger feel hot. If enough heat is transferred, your finger will become very painful, and you will drop the pin. The transmission of heat from one end of the pin to the other, and from the pin to your finger, occurs by conduction. Heat transferred in this fashion always flows from warmer to colder regions. Generally, the greater the temperature difference, the more rapid the heat transfer. When materials can easily pass through from one molecule to another, they are considered to be good conductors of heat. How well they conduct heat depends upon how their molecules are structurally bonded together. Table 2.2 shows that solids such as metals are good heat conductors. It is often difficult, therefore, to judge the temperature of metal objects. For example, if you grab a metal pipe at room temperature, it will seem to be much colder than it actually is, because the metal conducts heat away from the hand quite rapidly. Conversely, air is an extremely poor conductor of heat, which is why most insulating materials have a large number of air spaces trapped within them. Air is such a poor conductor of heat that in calm weather, the hot ground only warms a shallow layer of air, a few centimeters thick by conduction. Yet air can carry this energy rapidly from one region to another. How does this phenomenon happen? It's a hard word. Convection. The transfer of heat by the mass movement of a fluid, such as water and air, is called convection. This type of heat transfer takes place in liquids and gases because they can move freely, and it is possible to set up currents within them. Convection happens naturally in the atmosphere. On a warm, sunny day, certain areas of the Earth's surface absorb more heat from the sun than others. As a result, the air near Earth's surface is heated somewhat unevenly. Air molecules adjacent to these hot surfaces bounce against them, thereby gaining some extra energy by conduction. The heated air expands and becomes less dense than the surrounding cooler air. The expanded warm air is buoyed upward and rises. In this manner, large bubbles of warm air rises and transfer heat energy upward. Cooler, heavier air flows toward the surface to replace the rising air. The cooler air becomes heated in turn and rises, and the cycle is repeated. In meteorology, this vertical exchange of heat is called convection, and the rising air bubbles are known as thermals. Fun. We to finish that section. Look at me go. I'm just I don't want to read about this. It's about like radiation. I don't care. Like, I just want to get to the tornadoes. That's all I want. Let me skip forward here. Seasonal and daily temperatures. Why Earth has seasons. Oh, I'll read about that. Why Earth has seasons. Earth revolves completely around the sun in an elliptical path, not quite a circle, in about 365 days and 6 hours, 1 year, plus a leap day every 4 years in February. As Earth revolves around the sun, it spins on its own axis, completing one spin in 24 hours, 1 day. The average distance from Earth to the sun is 150 million kilometers, 93 million miles, because Earth's orbit is an ellipse instead of a circle. The actual distance from the Earth to the sun varies during the year. Earth comes closer to the sun in January, 147 million kilometers, than it does in July, 152 million kilometers. From this observation, we might conclude that our warmest weather should occur in January and our coldest weather in July. But in the northern hemisphere, we normally experience cold weather in January and we are closer to the sun, and warmer weather in July when we are farther away. If nearness to the sun were the primary cause of seasons, then indeed January would be warmer than July. However, nearness to the sun is only a small part of the story. Our seasons are regulated by the amount of solar energy received at Earth's surface. The amount is determined primarily by the angle at which sunlight strikes the surface, and by how long the sun shines on any latitude, daylight hours. Let's look more closely at these factors. Solar energy that strikes Earth's surface perpendicularly directly is much more intense than solar energy that strikes the same surface at an angle. Think of shining a flashlight straight at a wall. You get a small circular spot of light. Now tip the flashlight and notice how the spot of light spreads over a larger area. The same principle holds for sunlight. Sunlight striking at Earth at an angle spreads out and must leave a larger region than sunlight impinging directly on Earth. Everything else being equal, an area experiencing more direct solar rays will receive more heat than the same sized area being struck by sunlight at an angle. In addition, the more the sun's rays are slanted from the perpendicular, the more atmosphere they must penetrate. And the more atmosphere they penetrate, the more they can be scattered and absorbed, attenuated. As a consequence, when the sun is high in the sky, it can heat the ground to a much higher temperature than it is when it is low on the horizon. The second important factor determining how warm Earth's surface becomes is the length of time that the sun shines each day. Longer daylight hours, of course, mean that more energy is available from sunlight. In a given location, the more solar energy reaches Earth's surface on a clear, long day than on a day that is clear but much shorter. Hence, more surface heating takes place. From a casual observation, we know that summer days have more daylight hours than winter days. Also, the noontime summer sun is higher in the sky than it is the noontime winter sun. Both of these events occur because our spinning planet is inclined on its axis, tilted as it revolves around the sun. There's another figure. The angle of a tilt is 23.5 degrees from the perpendicular draw to the plane of Earth's orbit. Earth's axis points to the same direction in space all year long, thus the northern hemisphere is tilted toward the sun in summer, June, and away from the sun in winter, December. at that? Isn't that fun? So there's some fun little science. Let me find another little section to read. Wait a minute. Hello. Condensation, dew, fog, and clouds. Back to the clouds. Full circle. The formation of dew and frost. On clear, calm nights, objects near Earth's surface cool rapidly by emitting infrared radiation. The ground and objects on it often become much colder than the surrounding air. Air that comes in contact with these cold surfaces cools by conduction. Eventually, the air cools to the dew point, the temperature at which saturation occurs. As surfaces such as twigs, leaves, and blades of grass cool below this temperature, water vapor begins to condense upon them, forming tiny visible specks of water called dew. If the air temperature should drop to freezing or below, the dew will freeze, becoming tiny beads of ice called frozen dew. They just have such an easy name, and then they have hydrophobic. And obviously that means you don't like water, but like frozen dew versus dew. I'm just saying, okay? It's a stupid argument. I don't even know what I'm saying. I'm rambling. Because the coolest air is usually at ground level. Dew is more likely to form on blades of grass than on objects several meters above the surface. This thin coating of